Welcome to our channel. Watch the video until the end, leave a like, and subscribe to support us. For a long time, astronomy and cosmology were dominated by the concept of dark matter, which is said to make up the majority of the universe. Now physicists are finally moving away from dark matter and developing a new theory of gravity. This means that many of the old theories about the origin of the universe have been revised, and we are at the beginning of a new science. But what will our picture of the universe look like if there is neither dark matter nor dark energy? What role do fundamental forces and discoveries from the James Webb Space Telescope play? Did you also think that dark matter was real? You are not alone. The existence of this matter has long been considered by science as an obvious and proven fact. Yet many did not know that dark matter, like dark energy, has always been just a concept, a mere idea to fill gaps in scientists' explanations. And now researchers must realize that they might have made a mistake because the James Webb Space Telescope is showing us discoveries that contradict our old theories. Whether we're talking about the Big Bang or the formation of the first stars and galaxies, real images of space show us that the universe was much more developed 13.6 billion years ago than a Big Bang would have allowed. This universe does not seem young or as if it were born only 200 million years ago. Researchers have found a series of very advanced galaxies, and there is still no trace of the hypothetical first giant stars. On the contrary, more and more large, mysterious structures are appearing that do not fit the image of a young universe. Our universe must be older, or it might even be eternal. This means that many approaches in astrophysics have been based on incorrect assumptions for over 100 years, including dark matter. How did scientists arrive at dark matter? Who would have thought that the story of dark matter began with Sir Isaac Newton in the 17th century? Newton revolutionized our understanding of the natural world with his theory of universal gravitation. This theory simply states that all objects in the universe attract each other through gravity, which is proportional to the product of their masses and inversely proportional to the square of their distance. Newton's laws were able to describe the movements of the planets in the solar system with impressive accuracy for many centuries. But then, the first anomalies appeared that could no longer be explained by gravity alone. One of the first anomalies was the precession of Mercury's orbit in the 19th century. The French astronomer Urbain Le Verrier hypothesized that Mercury's orbit was influenced by the gravitational attraction of an unknown planet. This supposed planet called Vulcan was searched for intensely for many years, but only when improved telescopes clarified that there could be no other planet between Venus and the Sun was the Vulcan theory abandoned. However, the deviations in Mercury's orbit could never be completely explained. The term dark matter was first used in the 1930s by a Swiss astronomer named Fritz Zwicky. Zwicky studied clusters of galaxies and realized that the visible mass of the galaxies was not sufficient to explain the observed effects of their mutual gravitational attraction. He therefore suggested that there must be a form of matter not directly visible because it does not emit or reflect light, but that nonetheless had a sufficient mass to cause the observed gravitational effects. This was the true beginning of the idea of dark matter. Over the decades, further observations strengthened the hypothesis of dark matter, particularly in the 1970s, when Vera Rubin's observations of galaxy rotation curves provided much more evidence. These showed that stars in the outer regions of galaxies rotate faster than the visible mass would allow, thus indicating that there must be an additional mass not directly observable. Once again, dark matter came into play. Despite these observations and indications, dark matter remains one of the great unresolved issues in physics. Its exact nature has remained unknown until the end, even though we have made many attempts to detect it, and there is no direct evidence of its existence. Today, the existence of dark matter is being questioned by an increasing number of scientific environments, and the latest discoveries of the James Webb Space Telescope are one of the reasons. Discrepancies like the Hubble constant, for many years, further indicate that something is wrong with our cosmology. The Hubble constant essentially tells us how galaxies move away due to the expansion of the universe. Different measurement methods have given different results. Researchers refer to these differences as Hubble stress. In fact, the measurements should always be the same. It is very likely that errors have crept into our assumptions about the expansion of the universe that could have to do with dark matter and dark energy. Dark matter was supposed to explain the gravitational effects of the universe that cannot be explained by visible matter alone, while dark energy was used to explain phenomena such as the accelerated expansion of the universe. Since the Geneva particle accelerator has never been able to demonstrate the existence of these two forces, we must slowly rethink and find new explanations for the existence of the universe and the dynamics that guide it. An alternative explanation for gravitational phenomena is offered by theories like modified Newtonian dynamics, or MOND for short. This theory proposes that the laws of gravity need to be slightly adjusted in the presence of extremely low accelerations, such as those found in the outer regions of galaxies. This adjustment suggests that there exists a fundamental acceleration threshold below which Newton's laws of gravity no longer apply. On the contrary, gravitational forces behave a bit more strongly than previously described by classical physics. These effects are also possible in space. Some researchers even believe that there could be at least one other fundamental force in the universe that we do not yet know about, which might be involved in these slight deviations. MOND can almost perfectly explain why stars in the outer regions of galaxies rotate faster than the visible mass of the galaxy would allow, thus making dark matter superfluous for explaining the phenomenon. Moreover, MOND can also consistently explain the flat rotation curves of galaxies without the need for dark matter, where the gravitational force is not linear at very low accelerations but decreases more sharply. The theory emerged in the early 1980s and was proposed by Israeli physicist Mordecai Milgram. However, MOND never gained widespread recognition as, at the time, the scientific world still firmly believed in dark matter. Another significant development is TV's, tensor vector scalar gravity, which is a further development of MOND. Astrophysicist Jacob Bekenstein added scalar and vector fields to the current law of gravity to extend general relativity and explain various cosmological observations without dark matter. Although the theory is consistent, it too was not taken seriously, which may have been a mistake. Similarly, FR theories have slightly modified the general form of Einstein's field equations, changing the geometry of the space-time continuum, leading to altered gravitational dynamics on large cosmological scales. Scalar and vector fields can be considered as invisible forces distributed in space. Scalar fields act like variations in pressure or temperature, evenly distributed that are equally strong everywhere but do not have a sense of direction. Vector fields, on the other hand, are like the wind that not only has a force but also a clear direction in which it blows. These fields have to do with gravity or the processes of movement in galaxies, as they act as invisible helpers determining the speed and direction with which stars and other objects in a galaxy move. Imagine scalar fields giving stars a small push that makes them move faster and vector fields guiding them in a certain direction, just like the wind guides and governs a sailboat. In this way, these fields help explain some unexplainable cosmic dance movements of the stars, without the need for dark matter. All these alternative theories have long been considered in contradiction with traditional theories that, until recently, were considered almost incontrovertible truths. But now everything is different. On one hand, we are dealing with entirely new discoveries that are no longer consistent with old physics, and on the other, even established theories have never been able to describe and explain the entire universe. What role do Webb's discoveries play? Astronomy enthusiasts will already know that the James Webb Space Telescope is currently disrupting science. Galaxies like GNZ 11 or Maisie's galaxy do not match the image of the Big Bang that is said to have occurred 13.8 billion years ago. These two are not the only ones. In fact, researchers have found dozens of other galaxies that are at least the same age, if not older. If we consider that, according to previous scientific theories, these galaxies need billions of years to develop. Their birth time must be before the Big Bang, and this cannot be the case. Consequently, the universe is probably much older than previously estimated, or stars and galaxies formed more rapidly. However, there are still no conclusive concepts about this. This explanation is still preferred by many traditional researchers. For these scientists, it is difficult to move away from ideas like the Big Bang or the expansion of the universe. A person who has demonstrated that a little skill and an open mind are enough is Canadian researcher Rajendra Gupta. The astronomer from the University of Ottawa presented a new theory of gravity in which he combined the MOND theory with a variation of the cosmological constants. Cosmological constants are forces in space considered linear and thus used as standards. If we admit the possibility that these constants are a bit more flexible than we thought, the universe could be 26.7 billion years old or even over 40 billion. These hypotheses suggest an age of the universe significantly greater than that commonly accepted, which could rewrite many of our fundamental concepts about cosmology. With the contribution of new theories and the challenge of existing ideas, the field of astronomy and cosmology faces a potentially revolutionary period. The discoveries of the James Webb Space Telescope and other technological advances continue to provide data that could contradict or strengthen current theories. Every new observation that seems not to conform to expectations raises important questions and stimulates further research. Moreover, as the scientific community explores these new possibilities, it is crucial to remain open to debate and continual verification of hypotheses. Accepting the possibility that our previous understandings might require significant revisions is not just a demonstration of scientific humility, but also a crucial step toward a deeper understanding of the universe. In conclusion, science does not stop in the face of enigmas and uncertainties, but rather views them as opportunities to deepen our understanding of nature. Theories like MOND, TVs, and other modifications of gravitational laws, as well as new data from cutting-edge tools like the James Webb Space Telescope, push us to explore concepts that were once considered impossible or unrealistic. The current era may be remembered as a turning point in the history of cosmology, where old truths were questioned and new truths emerged from bold inquiries and open minds. Thank you for watching, and remember to subscribe to the channel to support us.